All righty. So let's talk for just a little bit here. I'm just going to bring this up. So I just became aware this morning that the second homework problem I messed up on, and it is actually not solvable, I do not believe, unless I'm missing something. It wasn't exactly the problem I intended. I forgot to change one variable. Let me show you here for just a second. Oops. Okay, so I had a couple of requests. One was in discussion to the C value. So let me bring this up so make sure we're on the same page here. Let's see how do I get rid of this little panel over here. I can do it. View, full view.
Just that arrow.
Right there, thank you. Okay, I know it was easy.
One more you can push.
One more arrow?
Down and bottom.
Push that down this one, and I'll get rid of it completely. All right. Yeah. It's kind of funny how easy things like that, when you get up here in front of people, all of a sudden they're gone, right? Okay, so let me bring up really fast and talk a little bit about problem one, because now we switched over to problem one where we're dealing with the SI system rather than the English system. The C values are going to be quite a bit different than what we worked in class. And I know some of you are like, well, that doesn't seem right, and it doesn't. Okay, so if I call those pipes, we're going to call the highest elevation 1, the elevation 20 is 2, and elevation 0 is 3. So I'm going to put that in here really fast. Let's see, we got like this D, L, and F. And so D for the first one, 0.08. Whoops. And the numbers block is on there. There we go. Okay. Jump down 0.08. D of, nope, I did that wrong again, didn't I? 0.1, 2 is 0.08, and 3 is 0.08. The length of the first one then is 200. The length of the second one is 200, and the length of the third one is 400. And the friction factors 0.015, 0.02, and 0.02. All right. So in calculating the C factor, we would go F times L over D times then 1 divided by 2 times, make sure you use the gravity for the metric system, that's a common mistake. So 9.81 times then the area, so the area is going to be pi divided by 4, the area squared, so pi divided by 4 times our diameter, raised to the square, and then I'm going to square the whole area. And that right there, that did not come out correctly either, did it? What'd I do?
I think you need an extra parentheses by around 2, maybe, right there. Is that whole term divided by that?
Well, not divide, I'm multiplying.
That is the value I got, just to let you know.
That is the value you got. Okay. So maybe it's semantical. Maybe
Yeah.
maybe we did it wrong in the office. Anyone else get that value? A couple of you did. Sorry, the value of 25,000.
Yeah.
Several of you got it? Let me just look at this again really fast. So F times L over D times 1 over 2G pi 4 D squared, and the whole thing squared, and my parentheses. I should just look at the solution, but G, and that is squared. That's raising the area, so I think that is correct. Oh, this is the reason why, because we've changed the notation of which was pipe 1 now, Samantha.
Oh, yeah.
So when I copy that down, now I do get that 100,000 for the second pipe. Yeah, so we changed the notation there. Okay, so now these are awfully large, which is to be expected because, once again, the metric system, the standard unit is meters. Well, 1 meter is significantly larger than 1 foot. And when you square that with area, and so when you go ahead and calculate the flow rates of this, you're going to come up with some really, really small flow rates. And you're going to say that's essentially 0. Well, it is as long as you're talking about meters cubed per second. When you think about a meter, 3 feet by 3 feet by 3 feet, bring that back to the English system. It's a lot of water. So sometimes in the metric system, to make things a little more realistic to us, we convert it to liters per second. Now the equations still use meters per second because meter is a standard length. A liter is not. That's like in the English system gallons. So it's like we do this all the time with our units, and I'm not sure why we do that. I think I bring this up in past classes, but when you go to the store and you buy a sack of potatoes in the SI system, what kind of measurement are we using?
Kilograms.
Kilograms, right? Is kilograms a measurement of weight? No, it's a measurement of mass. Newtons. We should be buying potatoes in newtons, or whatever else we're buying as a function of weight. It should be newtons in the SI system. We don't use that. We use kilograms, which messes up a lot of engineers because when you're not doing calculations in the SI system, you start putting kilograms in for a weight, and you're off by a factor of 10. So the same thing here is a lot of times we'll convert flow to liters per second, or when we go to pumps, we'll go back to gallons per minute. And not only do we change it from a length to a volume, which is perfectly fine, it's just another unit, we also change the time. Rather than seconds, it's gallons per second, it's gallons per minute. So just be really careful. So if you look at this and you calculate it, you're going to get really, really small values in cubic meters per second, and you're going to say, well, that's essentially 0. My system, is balanced out and close enough. But if you divide it or multiply it by 1,000, bring it to liters per second, you'll see that there's a huge differential there. So you still have to adjust. Now be careful when you start adjusting your hydraulic grade line at the junction too, because if you say, I'm going to jump up 2 meters, well, that's a huge change. You might have to go a fraction of a meter if you're relatively close. So feet, it's easier to go up 1 foot. That makes sense, 1 foot or 2 foot. But meters, I'm going to go up 2 meters, that's 6 feet, 6+ feet, right? So just a little bit of relativity there to kind of help bring that into perspective. Okay. Any additional questions on problem 1? Let me jump to problem 2. Did anyone get it to work out? A couple of you got to work out? Okay, well, we need to talk. Because maybe I'm not seeing something. I slapped this problem together on last week, I think, when I was in a hurry, and then we ended up extending our homework out a day. My intent was to make the hydraulic grade line at the junction 170, not the elevation of 170. So if you said, oh, the elevation is the hydraulic grade line, then yes, it is solvable. But in reality, the hydraulic grade line is not the elevation. The elevation is only one part of the hydraulic grade line, and you need the pressure. So I've introduced another unknown here. I've introduced the pressure at 1, and we also don't know the hydraulic grade line at C. So unless I'm missing something, we can get the friction loss through pipe C. So we know the flow rate, we get the friction loss. So we know the differential head. If you make the assumption that C is lower than A and B, then it's solvable. Okay, so let me say that. If we make the assumption that C is lower than A and B, then it's solvable. Or if it's higher, then it's solvable. But if we don't know if it's lower or higher, then it's not solvable. Okay?
If I can just interject there for a second, sorry. Where you can calculate the C value for it and you know what the Q value is, C times Q squared will give you what the head loss is through that drop, right?
Correct.
So if you calculate that and you know what the head loss for the HGL is for that section, you can automatically tell that the HGL must be lower than the other ones because of the value that returns.
Unless, Scott, I mean, you're exactly correct, unless the head loss is in the other direction.
Yeah, and I assumed that it was going down towards C after calculating that as opposed to coming back from C towards the junction. But yeah, I wrote that in, but yeah, that's the opposite direction.
So you are absolutely correct. If you know that C is absolutely lower than A and B, then it is solvable. But if you don't know that for a fact, then there's two answers. So that's not, I shouldn't say it's not solvable. I should say there's two answers. That's more appropriate. There's two correct answers. One is that C is higher and the head loss is going now from C down to the junction. And the other one is that C is lower and the head loss is from the junction going down to C. So does everyone understand that? So that would be a valid test problem if I told you, oh, C is lower or C is higher, then it's perfectly solvable. All right. My intent when I set this up was to make the elevation at the junction, to make the hydraulic grade line at the junction 170. Okay. I know some of you got that to solve, and I know you're not trying to create additional work for you, but I also want you to be able to solve this if you know the hydraulic grade line at the junction. So I'm going to extend the date on this, and I'm going to fix that problem, and I'm going to let you resolve that knowing the hydraulic grade line at the junction is equal to 170, and it falls right out. By the way, we talked about this on Monday. This is one of those problems where there is no iterative trial and error. It falls right out. It makes it really easy. Plus, if we get far enough today, I'm going to let you resolve problem number 1 using a numerical method. And then we can hand that in together. So you'll have both the hand solution and the numerical method, okay? All right. And I just realized I did not bring my handout from last time, or what we wrote last time. So I'm gonna have to start from scratch on that. But any other questions on the homework, questions or comments? I appreciate the feedback. If not, let me jump back over here and go through this. All right, so help me out here. When we finished up, I think what I've done is I've drawn 3 reservoir problem. Called this A. Came down to the junction. Called this B. I think I had C coming down this way. Oops. Trying to get into too big of a hurry here. And we labeled these 1, 2, and 3. Is that correct? Okay. And then we said that we could actually write the energy equation from A all the way to B. So we could say that the hydraulic grade line at A minus, and we're going to assume that A was higher. Did I have elevations on these?
That A was 100. C was unknown.
And C was unknown?
Yeah, and then we had the HDL at the junction of 82.
And that's where we ended? I didn't write the energy equation all the way from A to B? Oh,
No.
I'm going C now. All right. Okay. So let's rework this. So let's do that. And we're going to make this one, I don't know, say 30, 35. Not feet or meters. We're just going to say 35 because this could be SI or the inverse system. So this is a different problem. So what I finished on, I guess, last time was a little bit of information to show you that the homework problem was how to solve the homework problem. And then I messed up on the homework problem. So reconfigure this, and we're going to talk about how we can solve 3 reservoir problems numerically, because this is going to help us understand pipe networks as well. So the 3 reservoir problem is a great problem to kind of cut your teeth on and help us better understand pipe networks. Okay. So look at this. I know that the flow goes from A down to the junction, and I know that it goes from the junction down to C. But I don't know what's going on at B, right? Hopefully we've clearly identified that fact. We don't know what's going on at B. We don't know if the flow is coming from B or to B. So I'm now going to write my equations from A to B, the energy equation from A to B. All right. So I start off at A, the hydraulic grade line A, and I'm going to go with the flow. So with flow is negative, and against is positive. And so going with the flow is minus, so now I'm going to get C1 times Q sub 1 squared. And that takes me to the junction. And now I'm going to go up to B. Well, I don't know if it's plus or minus, because I don't know if I'm going up the hydraulic grade line or down. So it's going to be plus or minus C sub 2 times Q sub 2 squared. And that's going to take me then to the hydraulic grade line at B. Now I can do the same thing, going from A to C. So the hydraulic grade line at A minus C sub 1 times Q sub 1 squared. And then I get to the junction. Now I'm going down to C. I know that flows that direction, so it's a minus C sub 3 times Q sub 3 squared is equal to the hydraulic grade line at C. Okay. Now I could also write from B to C, but I really don't get any additional information when I go from B to C. When I say no additional information, it's one additional equation, but it doesn't have anything new in it. It has the same information of Q sub 2 times C sub 2, well, C sub 2 times Q sub 2 squared, or C sub 3 times Q sub 3 squared. So these 2 energy equations describe the energy in that system. Going from B to C is a redundant equation. It doesn't add anything to my system. But I do have one other equation that I can add to my system, and that equation is Q sub 1 plus or minus Q sub 2 minus Q sub 3 equals 0, using then my sign notation that in is positive and out is negative. This is for continuity. This up here is energy. My original one was the energy coordinate system, and this one is the continuity coordinate system, Laura.
So how come we didn't use any formulas like with the HDL at the junction? Just because it's not known in this one?
it may not be known. So what we're trying to do is simplify this problem so we can solve it numerically. Okay. And if I had known,
What are we solving for?
we're solving for the unknowns are the flow rates. The unknowns, Q1, Q2, Q3. Okay. Good question. So Laura, let me show you. So if I had taken the hydraulic grade line at A minus C1 Q1 squared, is it? Does it freeze everything? Goes online, make some sort of motion.
Yeah, I can see movement.
Okay, they're moving.
Yeah, it's just the heads up display that you're using.
Okay, let's shut it down and start it back up.
So when we don't have the junction, hydraulic grade line at the junction given.
At the first problem I went over in class, we didn't have that either. That was just what we were going to.
We just had it given in the one that looked just like this on Monday. But we took it out for this one.
Right, so go back to the first one we did in class on Monday.
Yeah.
Or for the first
that
one you
one.
did a homework problem. We know that the hydraulic grade line at junction is real and exists, we just didn't know the value. And so we did this trial and error procedure where we assumed the hydraulic grade line at the junction was equal to the middle reservoir, right?
Mhm.
Okay, so in this problem, we're going to, okay, there we go. So look at this. All we're doing here is a little bit of substitution. If I rewrite my original equations, hydraulic grade line at A minus C1 Q1 squared equals the hydraulic grade line at the junction. And then I write the hydraulic grade line at the junction plus or minus C sub 2 times Q sub 2 squared equals the hydraulic grade line at B. And now if I just do a little substitution and because these two are equal, and now bring this other term over to this side, and if it's plus or minus, it becomes minus or plus, right? No different there. So this equation now becomes the hydraulic grade line at A minus C1 Q1 squared. Once again, plus or minus C sub 2 times Q sub 2 squared is equal to the hydraulic grade line at B. And isn't that then exactly the one that we have right here? Okay. So we have just eliminated the hydraulic grade line at the junction. It's still real, it still exists. We're not worried about it right now. We can solve for it later on. We're trying to simplify our life to make it easier to solve. And our second equation here would be the same thing as if I had took the first equation going from A to J and the second equation from J to C and combined those two together. That gives me this second equation right here. Okay. So now I have three equations, three unknowns. Okay. And I need to solve these. So what we're going to talk about today then is a little numerical technique. Unfortunately, we had, given all the constraints we have on credits, and this is standard across the United States, undergraduate engineering courses have cut back on the number of credits required to graduate. We had to drop something, and the little numerical methods class we had to get dropped, all right? But nonetheless, understanding how to solve an equation is a good thing. So if I have these three equations, I'm going to rewrite them up here. Q1, well, before I do that, let me do this. If I gave you an equation set, 5x sub 1, I don't want x sub 1 there. Okay, 5x, let me just start over here. 5x minus 2y plus 3z equals 10. Negative 2x plus 3y minus 1z equals -2, and 3x minus 5y plus 4z equals 5. If I gave you that set right there, how would you solve it?
Matrix manipulation.
Matrix manipulation, and
Or if you put like two of the equations in terms of one variable, and you can plug it in.
okay, or back substitution.
Mhm.
So matrix manipulation or back substitution, either one of those would work just fine. And there are correct ways to solve this, and they work because this is a linear system. Remember one of your favorite math classes, linear algebra? And I say that kind of sarcastically. Linear algebra is actually very practical, and it has a lot of uses. And depending upon what I've heard, depending upon who you take it here, you get the applied side or you get the theoretical side, right? But the applied side, we use it in structural analysis, right? I'm assuming most everyone here is taking structural analysis. We use linear algebra all the time. And linear algebra is nothing more than matrix manipulation or back substitution. And so if I wanted to solve this, I could turn this into a simple matrix of 5, -2, and 3, -2, 3, and -1, and 3, -5, and 4, with then my unknowns being x, y, and z, my solution vector. And my b vector then is going to be 10, -2, and 5, right? Of the form a times my solution vector is equal to b, or my solution, my coefficient matrix, sorry, I said that wrong. My coefficient matrix times my solution vector is equal to the b vector. I forget the technical name for the b vector, but that's this over here, right? And therefore, that's the linear algebra I'd use to solve this problem, right? So it's fairly straightforward, okay? Now the question is, well, looking at this, I'm trying to find the flow rates, all right? But the problem with my equation as it is now, compare that to what we had before, and it is now nonlinear in the variable I want to solve for. Q's are squared. So it's nonlinear. So I can't use linear algebra. It's not quite as simple. I can rewrite this. Watch how I rewrite this. I'm going to rewrite this then as Q sub 1 plus or minus Q sub 2 minus Q sub 3 equals 0. My next equation I'm going to write as negative C sub 1 times Q sub 1 squared plus or minus C sub 2 times Q sub 2 squared. There is no Q sub 3 in that equation. That then equals the hydraulic grade line at B minus the hydraulic grade line at A. And the next equation, okay, negative C sub 1 Q sub 1 squared. There is no, so 0 in here. There's nothing for Q sub 2. Minus then C sub 3 times Q sub 3 squared is equal to the hydraulic grade line at C minus the hydraulic grade line at A. I'm sorry, I didn't put that up there, okay? So there's my three equations just rewritten. And if you notice now, I have Q sub 1, Q sub 2, and Q sub 3, which correlate to X, Y, and Z. Those are my unknowns, three of them, just like X, Y, Z. But because they're nonlinear, I can't use the matrix method to solve this unless I linearize the equations. I want to linearize my nonlinear equation. So this is a numerical method. Linearize the equation and then do trial and error. We had to do trial and error by hand, so it's not uncommon. We have to do trial and error within the computer to solve this. All right? So how do I linearize this equation? Well, if I take this term right here, and I'm now going to linearize. In other words, I want to make the unknown value to the power of 1. All I want to make the unknown value the power of 1, and then it's linearized. Now, there's a lot of ways to do this. We can actually take the derivative of that and then use the derivative to tell us which way we need to go when we're calculating our different flow rates. And they call that the Newton-Raphson method. We're not going to get into that. We're going to do a simple linearization. So this doesn't work on all problems, but it works for actually a fair number of problems. If I want to linearize C1 Q1 squared, it simply becomes C1 times Q1 old times Q1 new. Oh. To where C1 times Q1 old is known.
Wait, so what is Q1 old versus Q1 new?
Okay, good question. Good question. We're going to start off with Q1 old being a guess. Whatever you want. Okay. So Q1 old. So right now I'm just going to put it in general terms. Q old, because it could be 1, 2, or 3, right? Q old is a guess. And from there we solve for Q1 or Q new. We're just going to say Q new. It's a little bit of programming language here then. Then Q new becomes is equal to, then Q old is equal to Q new. And then we repeat.
Sorry, you keep guessing until they equal each other?
No, you don't keep guessing. So I'm glad you brought that up because this is an interesting distinction. We guess once, and then we solve for Q new. Q new becomes our new guess. We don't guess a new value. Q new becomes the new guess. And then we take that and solve, that becomes Q old. And then we solve for Q new again, and that becomes the new guess. So the new guess is built into the process. Just like when we did pipe networks with the friction factor, we started with a guess. Friction factor is equal to 0.2 or whatever you wanted. And then you solve for the flow rate. And for the flow rate, you went to the Moody diagram and found the friction factor. That became the new guess. You didn't pick a new guess. That became the new guess. And then we went through it again. We just iterated. Okay? So now on this, we're just going to iterate, and we're going to let it set the new Q value. And just keep iterating until, repeat until Q new is approximately equal to Q old. To where it gets down to some level, we say that's close enough. And we're done. Okay?
So we solve for Q new, but what do we set it equal to? That whole equation right there?
Once we solve for Q new, we let that equal Q old.
No, I mean like when you solve it, because right now it's just C1 Q1 old Q1 new.
Right.
And then equal to what?
So this right here, this term right here becomes this term.
Oh, so that's an equal then?
Yes, it becomes. You could say equals if you want to. Yeah. They are equivalent. So now I'm going to stick this up in there. And by doing that, I've linearized my equation. Well, how are we doing there? Does that make sense?
Well, so we would
Let's
have to do the
read.
same thing with Q2 then?
Yes. So let's rewrite that matrix. Okay. If I rewrite my matrix now, or I rewrite those equations. I haven't written the matrix yet. So if I rewrite those equations, I get Q1 plus or minus Q sub 2 minus q sub 3 equals 0. And over here, I get minus c sub 1, q1. To simplify my notation, would you let me say that q old equals q prime? This is a simplification, right? All right, so we're going to let q1, so q1 prime times q1, where q1 prime is just q old. Make sure that put that in your notes. It's not the derivative, or it's not raised to the first power. That's prime. That's equal to old. So negative c1 times q1 old times q1. Okay, and then I get plus or minus c sub 2 times q sub 2 prime times q sub 2. Minus 0 equals the hydraulic grade line at B minus the hydraulic grade line at A. And then the next one I'm going to get minus c sub 1 times q sub 1 prime times q sub 1. And then 0 for the next term, minus then c sub 3 times q sub 3 prime times q sub 3 equals the hydraulic grade line at C minus the hydraulic grade line at A.
You don't have to do the Q prime if there's not a C, like the first line, you don't have to do that.
So the continuity equation is already linear, right?
Okay.
It's already in linear form. It's just the flow coming in minus the flow going out. There is no q squared. So we don't have to linearize that equation because it's already a linear equation. Again, let's see. Okay, good. So now you'll notice that I can take, I really wish the colors would show up better up here, but I can take, now what's the coefficient out in front of Q1? 1, right? And the coefficient then out in front of this one is also 1. Include the signs there. So I could rewrite this then into my matrix form of 1 plus or minus 1 minus 1. And then down here, I'm going to get negative C1 times Q1 prime, negative plus or minus C2 times Q sub 2 prime, and 0, and negative C sub 1 times Q sub 1 prime, and 0, and negative C sub 3 times Q sub 3 prime. That is my coefficient matrix, and I multiply that by my solution matrix, which is going to be Q sub 1, Q sub 2, Q sub 3, and that is going to equal then 0. And then the next row, the hydraulic grade line at B minus the hydraulic grade line at A. And then the next one is the hydraulic grade line at C minus the hydraulic grade line at A. So now that we have that and everything looks good like it's in matrix form because we know the hydraulic grade lines at our reservoirs, we know we're looking for the 3 flow rates, and we have our coefficient matrix, we know the C values, but we still have this pesky plus or minus term, right? Pesky plus or minus term, and if I went back to my 3 equations, my 3 unknowns, you think back to statics. And you can solve for 3 forces or forces in the 3 directions, right? And if you happen to you have to assume a direction. If you have to get that direction, if you assume it wrong, then the answer comes out negative, right? The answer comes out negative. Well, this is kind of the same way, except for when we linearize it, remember that q squared, doesn't matter if it's negative, it becomes positive. And likewise, if I take q times q, because I have q old and q new, if they're both negative, they become positive. And now I've killed the direction of my system. So I have to have a way to maintain direction in my system. All right? How am I going to maintain direction in my system so that if I'm solving this and it says you've got one of the flow rates backwards, that it will come out negative in the end? So that's another numerical trick. Look at this. If I take q squared and let it equal or let it become q old times q new, I have maintained, this is to maintain the value, the magnitude. That's the word I'm looking for. Maintain the magnitude. But if I go q squared and I let that become the absolute value of q old times q new, now I have maintained direction too. By placing the absolute value on that, I have maintained the direction that my solution gives me. Because think about this, if q is positive, down here, if q is positive, that still comes out positive. If q is negative, then I maintain my negative value. That should be q now. Right? So I've preserved the direction in my numerical method because I'm doing an iterative process. I'm solving for q, letting that become my old value, repeating, solving it again. And I just let it go around and around until those two reach approximately the same value. And by taking the absolute value of that, I maintain, if it flips on me, I maintain that. So now I can rewrite my matrix. And my matrix then is going to become 1, 1, negative 1. Because my linear system is going to work. So I'm going to assume, let me go back to my original plot here, or my original diagram. Okay. If I assumed actually, I guess I assumed the other direction, didn't I? Because I made it positive. If I assumed it was going from J to B, then I would come down here and I'd say, well, that's a negative, and I would make this a negative value. So I make the assumption, I think the flow is going to B. So with my coordinate system, with the flow is negative. So I come down here and make the flow negative there now. I make that assumption. And now I can put in the rest of my values. I'm going to do negative C sub 1 times the absolute value of Q sub 1 prime, which is Q old. Okay. Now I don't necessarily need to put it right there, but this is good practice for when we get to networks. Because I'm really only worried about B. So I really only need the absolute value on B. But this is good practice because when we get to pipe networks, there's going to be multiple pipes and we may not know the direction of the flow. So I'm just trying to set you up for success. And then the next one, if I make the assumption, oh wait, I just made a mistake, didn't I? Oh, that's right. I said it was going from B, so it's going out. Here, I made the assumption that it's going with the flow, with the HGL, so it's going to be now negative again. So this is going to be a negative C sub 2 times the absolute value of Q sub 2 prime, and then 0 for the last term. And for my third row, negative C sub 1 times the absolute value of Q sub 1 prime, 0 for the next term, and negative C sub 3 times the absolute value of Q sub 3 prime. And that becomes then my coefficient matrix. And Q sub 1, Q sub 2, Q sub 3 is my solution vector. And then that's going to equal the same thing that I had before. 0 for the first row, hydraulic grade line at B minus the hydraulic grade line at A for the second row, and the hydraulic grade line at C minus the hydraulic grade line at A for the next row. And now I have linearized my system. And now I can use vector methods. I can use matrix calculation, linear algebra, to solve this system. And I'm going to solve it, and I'm going to come up with my new values. I'm going to take those new values, plug them back in here, and convert them over into the old values, create a new matrix, solve this system again, and just keep solving it until it converges. Okay. Any questions on that?
I'm still a little confused on how you get your Q olds when we don't know Q1 or Q2 and they're both in the same equation, or like Q1 and Q3.
So we're going to take an initial guess at the start,
Both of them?
all three of them. We're going to say Q1 is equal to 1, Q2 is equal to 1, Q3 is equal to 1. Now, if you want your solution to converge faster, you're going to make them. You're going to meet continuity at the junction from the get-go, but you don't have to. So you can just say let them equal 1. It's a guess, and then we'll let the system solve it for us. So we take a guess. Q1 is equal to some value. Q2 and Q3 the same thing. Plug it into our equation, solve for Q1, Q2, and Q3.
Oh, we don't do anything up there,
Where?
like before our matrix. So basically,
No,
we
so
plug it into our matrix and then we
yes.
solve over and over.
So this is the matrix that we're dealing with now again. And we're just going to iterate now as we solve for Q1, Q2, and Q3 and keep updating those as the new values. Now there's one little caveat, and we're not going to have time today to go through it, and I'll talk about that on Friday then, okay? But this is the procedure that we go through. All right. So I didn't get far enough to show you an example on the computer. So the homework then that was due today, we're going to make that due on Friday, and we're going to fix problem 2. So the hydraulic grade line at the junction is equal to 170, not the elevation. Okay. And then I'll also give you an elevation because I want you to finish the other problems where you figure out the pressure of the junction as well. But let the hydraulic grade line equal 170 and solve it, and I'll correct that and repost it. That will be due on Friday. If you've already uploaded it, that's fine. You should be able to reload it. Your latest version, not a problem. Okay, so
Are we okay to just leave our old special problem 2 solution on there and to just like add a second section
Yes, that's fine too.
so the grader knows that there's going to be more than one answer to problem number 2 because there was 2 different questions asked?
Yeah, I'll try to remember to tell the grader. If the grader takes points off, you just let me know and I'll fix it. Okay. All right, have a great day. I'll see you on Friday.
Have any control over when they upload the video?
Yes, I do.
So,
Hold on a sec. Let me do this right here. Otherwise, we'll skip this.
the one from last Friday is not up. And I was on the road, and that's the first part of this problem, so I was having trouble getting started on it.